Hey everyone, welcome to Code Harmony. Today we are going to solve LeetCode Problem ID 2302. Count subarrays with score less than k. This problem has been asked in companies like Google, Meta, Pinterest, and it is based on the concept of sliding window. It is marked as hard, but it will be easy to understand. Let's have a look on the problem statement. The score of an array is defined as the product of its sum and its length. This is something given in the problem statement. An example is, let's say this example array is given to us. Then score of this array is sum of all the elements in the array multiplied with the length of the array. 1 plus 2 plus 3 plus 4 plus 5 into 5, which is the size of this array. 75 is the score. Now what we have to do is, given a positive integer array nums and an integer k, return the number of non-empty subarrays of nums whose score is strictly less than k. Now if we have a look on this example, in this example we are given integer array, and from this integer array we need to count, or you will need to return the number of non-empty subarrays. Non-empty subarrays means at least one element is there, and number of those subarrays, just count of how many subarrays are following that condition. And thus the condition is that score of that subarray is strictly less than k, not even equal. And score, the definition of counting score is already given in the problem statement. The score is sum of all the elements in the subarray multiplied with size of the subarray. So return the count of all the subarrays whose score is less than k. So this is our problem statement, and the k is also given to us. And let's have a look on the constraints. Length will go till 10 to the power 5. Every element is 10 to the power 5 and its positive value starting with 1, and the k value is also going to be the same range. So here it's 10 to the power 5, and if we try to think in terms of brute force way, what is going to be the brute force of this? As a summary to the problem statement, we are requested to return the number of non-empty subarrays whose score is less than k. K is given to us, and score we already discussed how to calculate that. For any subarray, let's say that if I choose the subarray 2, 1, 4, then score of this subarray is 2 plus 4, 1 plus 4 into 3. 3 is size of the subarray. 7 into 3, 21. So this is the score of this subarray. Now as we have to calculate the number of subarrays, why not we just check for all the possibilities, check every single subarray. What is subarray? A piece of continuous piece starting from any index and going till an index. And if we have to calculate all the subarrays, we can use two nested loops to figure out these two indices. First loop, let's say starting point of any subarray, that can go from index 0 to index n minus 1. And what about the ending position of that subarray? Ending position will start from I and can go till n minus 1. If I just try to write the pseudo code for the brute force, it will look something like this. We are checking every single subarray. Subarray is starting from any index, that is, let's say I, and I value can go till less than n, which is n minus 1, last index. And for every corresponding I will have a j pointer which can start from I, because at least one element should be there in the subarray. It will start from I, it will also go till less than n. Now using these two loops, at this position we have my subarray. This is my subarray. For subarray, to check the condition, what I require? I require the running sum, current sum of that subarray. Current sum. And what is the length of the subarray? Length of the subarray we can directly figure out. Subarray is starting from I and going till j, so the length will be j minus I plus 1. This is my length of subarray. And what is the sum? If I just use another loop to calculate the sum, it will go order of n cube, but we can avoid that by calculating the running sum when we are in the second iteration. In the second iteration, so before the second iteration, current sum is 0. Current sum of this subset is 0. Subarray is 0. And when we are doing this iteration, I will keep on doing current sum plus equal to nums of j. And now we have sum of subarray starting from I till j, and we are checking every possibility of j. Currently I is 0 and j will be 0, and then j will be 1, j will be 2, and so on. And meanwhile we'll keep on capturing the current sum. So I have the current sum, and the condition is, what is the condition? Current sum multiplied with length of the subarray. Length of the subarray is j minus I plus 1. This value should be less than k, not crossing k, not even equal to k. So if this condition is true, my answer is incremented. I have got the answer. Otherwise, what I have to do now? Otherwise, we can't just continue with this loop, because let's say if the subarray 214, if the 214 subarray is not going to give the answer, it means if the sum of all the elements are crossing k, if I have one more element, let's say even that is 1, so all of those subsequent subarrays are going to cross the sum, cross the value of k. So there is only one condition. We have to break checking for all the loops. Now this will be our brute force, that checking every possibility, every subarray from I to j, and in my second loop I can calculate the running sum, and on the basis of running sum I can check my condition. So this is the first loop and this is the second loop, and my current sum I'm calculating, and this is the condition. If this condition is true, I'm incrementing the answer. Otherwise I'm not going further, I'm just breaking it. This is the breaking condition. Now I hope the problems, this brute force will be clear to you. It's nothing, just we are doing like a brute force way to check every single subset, every single subarray. So here, what is the time and space complexity? One iteration for this can go till around an order of n time. This can also go order of n time. It will be order of n square time. And what about the space? Are we taking any space? No. It's a quadratic time and constant space operation. But our constraints are going till 10 power 5. So 10 power 5 into 10 power 5, 10 power 10. This is going to give us TLE when we are submitting it on our LeetCode. So it means that quadratic time we cannot afford. We have to somewhere think in terms of linear fashion. And here see, the main idea is that we are just calculating the number of subarrays. We are not calculating the actual subarrays. Now we will try to have a look on the optimized approach. Here n square possibility is not working because that is going to give us TLE. We need to think in terms of some linear fashion, and here the basic idea of that is we are only concerned about the number of non-empty subarrays. We don't require those actual subarrays. So here let's say that my array is starting with this. If I ending at this position, it is valid. If I am ending at this position, it is also valid. Why? Because let's say initially when j was at 0, so 2 into 1 is less than 10, valid. So now current sum is 3, window and subarray length is 2, 3 into 2 less than 10, valid. If I try to expand it again, my j is at this position, 4 plus 1, 5, 6, 7, 7 into 3 less than 10. This is invalid. So here this case is not correct, and here I don't need to capture any answer. But let's say if I am at the previous case, if I am at this case where my window is valid, here what are the possible subarrays out of this window? Because after this we are going to expand it, explore the next value of j. So starting at I equal to 0, I am going to capture every single subarray. That every single subarray is either 2 and 2, 1. So index 1 is done. If index 1 is done, then I can easily move further and explore other possibilities. I'll just increment my j and try to adjust the window to make it valid. See, we in this case are going to apply something known as sliding window. And to get a basic idea on the sliding window, what we do is we explore every single window using 2 pointers, I and j. And whenever this window is valid, when this window is valid, then we are going to capture it. So our first aim is always making this window valid, and second aim is once it is valid, then just capture it. So these are the two main idea behind implementation of any sliding window approach. First of all, make the window valid, and then if the window is valid, then capture. But here in this case, what I'm doing is I'm trying to get the maximum possibility I can get for any value of I. For value of I which is 0, maximum possibility I can get is this. If this is the maximum possibility, now I can check every single subarray starting from I equal to 0. That is, how many subarrays can be there? Starting with I equal to 0, 2 is there, 2, 1 is there. So how many are these? So these are the length equal to the length j minus I plus 1. So j minus I plus 1 number of subarrays are valid, right? Because if the sum and the length is less than k for this section, it will be less than k for every other section, because we have positive number and we are reducing something, so we are definitely going to reduce a value from the sum. So here like just apply the sliding window approach. First one is make the window valid and then capture it. Once we have done this, it means we are done with this current window of I. Then we can go greedy and we can increment our j value so that we can process other options as well. Why we are not capturing one by one? Because in that case our sliding window is not going to help. We have to check for every single possibility, because once every single possibility is done for I, only in that case we can explore further windows. Otherwise moving further is going to lose some of the cases. Let me show you again. 2 1 4 3 5 2 1 4 3 5. So how do we build our sliding window approach? Let's say this is I and this is j. First of all, I need to make it valid, and for that let's assume that from I to j, whatever is the subarray, this might not be valid. So to make it valid, the current sum, let's say the current sum is cs, into what is the length of the sliding window, j minus I plus 1. This portion, this is score given in the problem statement. This score is less than k, then it is valid. If it is greater than equal to k, then it is not valid. So while this window is not valid, try to increment I pointer, because whenever it is valid, we have captured for I. And if we are incrementing I, so current sum minus equal to the value at I. So this is something making it valid. Make valid. And if it is valid, it means from I to j, this window is valid. If this window is valid, just capture the sum. And how do I capture the sum? J minus I plus 1. This is sum of all the subarrays which are valid. So this is something I can capture in my answer. If I do the dry run, initially I is equal to 0, j is equal to 0. And once we have performed these two steps, then I can increment my j plus plus, and here I can include j, current sum plus equal to whatever value of j I am having. And this is something I will be doing while j is less than n. Let me move the example to some other places. 2 1 4 3 5 2 1 4 3 5, and here I is equal to 0, j is equal to 0, current sum is equal to 0, and answer is also 0. So initially I will just include the current element, right? And our framework is something like this: include, make valid, then capture. So make valid and capture, these are the two important steps. So firstly, if I include it, current sum will become 2. Then make it valid. So while it is not valid, make it valid by reducing I pointer, but it is already valid, so this step will not do anything. Then just capture it. Capturing means capturing all the subarrays starting from I, and that is j minus I plus 1. So answer plus equal to j minus I plus 1, which is 1. So answer will be 1 in this case. So if answer is equal to 1, just increment your j pointer. J pointer is at this position. Here current sum is 2 plus 1, which is 3. Current sum is 3, and while 3 into 2 greater than equal to 10, 3 into 2 is 6. Score is 6, so it's already valid, so no need to make it valid, and let's just capture it. Capturing means j value is 1 minus 0 plus 1, which is 2. So 2 will be added to the answer. 1 plus 2, which is 3. So as of now we have 3 subarrays which are going to give us valid answer, and those will be 2, 2, 1 and this 1. And now I need to increment my j pointer. J pointer I have incremented, and here what is the score? Score is 2 plus 1 plus 4, current sum plus 4, which is 7. 7 is the score. And what is the window length, subarray length? J minus I plus 1, which is 2 plus 1, that is 3. So 7 into 3, which is 21. 21 is greater than equal to k. 21 is greater than equal to k, so it means I have to make it valid. To make it valid, just increment I. Increment I by reducing the value of I from the window. So current sum was 7. When I incremented I, it became 5, and the window length became 2. 5 into 2. Still 5 into 2 is greater than equal to k. Equal to is also there. So again I need to make it valid. To make it valid, I need to increment my I. I and j both are at 2. So current sum is 5 minus 1, which is 4. Current sum is 4. And the window is, j is at this position. J is at 2. 0, 1, 2, 3, 4. J is at 2, I is at 2. So if both are 2, then what is the length? 2 minus 2 plus 1. 1 into 4. 4 is less than 10. So now the window is valid, and I need to capture it. Capture means 1 minus 1 plus 1, which is one item I need to capture here. So answer will be 4 now, and current sum is 4. Now increment the value of j. J is 3. So 4 plus 3, that is 7. 7 into 2, which is again not valid. To make it valid, increment I. So this 3 subarray 3 is valid. Subarray 4 was something we captured. So here the window subarray length is 1 and subarray sum is 3. 7 minus 4, which is 3. So it was 4, and then it became 7. It again became 3. Now 3 is something which is my current sum, and the current window is this I equal to 3 to j equal to 3. So this is going to contribute 1 to the answer, and again the last one will be j is here, and 5 plus 3 into 2, which is crossing the limit. So increment I as well. But in this case I am not going to capture this one as well. This is 5. Okay, this one I can capture, because current sum is 8 and then 5. Current sum is 5 into 1, which is less than 10. So this is valid. If it is valid, just capture it. J minus I plus 1. Capture 1. So it will be 5 and 6. So 6 subarray will be there, and those 6 subarrays are 2, 2, 1, and then 1, then 3, and then 4, and then 5. So these are the 6 subarrays which are giving me good score or score less than k. So this is how we can do or apply sliding window approach here. And in the sliding window approach, this is going to be our main idea. While it is not valid, just make it valid. Otherwise, if it is already valid, then just capture it. But let's discuss one more important case where the example is 2, 1, 4. 2, let's say instead of 1 we have 11, then 4, then 3, then 5. In this case, when I'm here at this position I, my j is at this. I need to capture it. 2 will be captured. After that I will increment j. Incrementing j, then this window is not valid. If it is not valid, I will increment I. But I and j, I is pointing to index 1 which is having element 11 and j is having element 11, but the value of k is 10. In this case, this is also not valid. This is also not valid. So it means this condition will be compared at the position where I and j are equal. So here this is the special case where I is equal to at index 1 which is 11, j is also at index 1 which is 11. What will happen in this case? We don't have to do anything. Our condition is good enough to take care of this case. I and j, what is the current sum? That is 11. What is the length? That is 1. If it is greater than or equal to 10, it is invalid. If it is invalid, increment I. If I am incrementing I, my I pointer will be at this position. If I is at this position, j is at this position. In this case, my answer should be incremented by 0 because there is no subarray. So here j is 1, I is 2. So length is j minus I plus 1, which is 1 minus 2 plus 1. It will automatically be 0. If we are encountering any element which is equal to or greater than k, in that case our condition is already handling that. So always remember, whenever we are having a sliding window, our main idea is that whenever we have to somehow make the window valid and then capture it and then do something, right? So this is the main idea. And okay, let's implement this code. And what is going to be the time complexity? See, sliding window, we are having 2 pointers. Both the pointers are going from 0 to n. So time complexity in this case is going to be order of n. And what about the space complexity? Constant space solution it is. Let's have a look on the code now. Here this is the brute force of the solution. In this brute force I'm checking every single subarray starting from index I and going till index j. So j will start from I and going till n. So these 2 nested loops to check every single subarray, and for every subarray I am maintaining a running sum which is current sum of that subarray. Every time I am incrementing the current sum value with the current element at index j, and then this is the condition to check whether the subarray is valid or not. Subarray is valid if the sum of that subarray, that is current sum, into length of that subarray, that is j minus I plus 1. If this multiplication is less than k, then this subarray is valid and increment 1 to the answer. Otherwise just break it. No need to explore further starting with this I and maintaining it as a long variable. So let me run over sample test cases if it is working fine or not. But the solution is order of n square, and order of n square is going to give us TLE. Here the sample test cases are passing, but when I submit it, as our input constraints are too large, 12 to 10 power 5, we might get TLE. Yes, we are getting TLE, and to avoid TLE, we need to implement the brute sliding window approach. Now let's implement our sliding window approach. In the sliding window, I need to maintain 2 variables. First one is I is 0 and j is also 0. While j is less than n, I need to do something. I need to keep capturing my window. Okay, answer is already there, current sum is already there. Firstly, let's include the current element. Including the current element mean current sum plus equal to nums of j. Then make window valid and then capture. In the end, increment j++. And whatever answer we are going to capture, that is something we will return from this program. Okay, everything is looking fine. Here, how do I make the window valid? While let's say current sum into what is the length, j minus I plus 1. If this product is less than k, it is valid. But if this product is greater than equal to k, it is not valid. If it is not valid, then increment I. But before incrementing this I value, I need to reduce the I value from the current sum as well. Current sum minus equal to nums of I. So here I have dropped one element from the left side of the window, and I will keep on dropping until this window is valid. And this is also going to cover the case where my single element is itself greater than k. In that case, I is going to cross j. Window is valid. Now it's the time to capture. To capture, we just have to capture all the subarrays. Let's say 1, 2, 3. 1, 2, 3. They are valid subarray. Valid window. In this valid window, it means starting from this index current element, that is starting from 1, we have to capture every single array. Every single array means from 1 to 1, from 1 to 2, from 1 to 3. J minus I plus 1. J minus I plus 1. So this is something we need to capture. So this template itself is more than sufficient for you to become an expert in sliding window. Answer plus equal to this. While it is not valid, just make it valid. And this is the current sum. That's all I need to do. Let's run over sample test cases. Nice. This is working fine on sample test cases. Let me submit again. I'm submitting this sliding window approach now. And now this is 100% faster. Beats 100% of Java solution. Thank you guys. I hope you understood the approach. In case you get any doubt, you can comment down below or discuss in the Discord community. I'll be happy to help. Bye bye.